before we get into the actual hands-on examples, let's talk about where metalogs work and where metalogs don't work, and where you need either further modeling or something else. And there are two categories of places where metalogs don't work, or they won't work well. Let's put it that way. And these are, for example, mixtures of continuous and discrete distributions. Metalogs are smooth and continuous, and the more continuous and the more smooth your data is, the better the metalogs will work, virtually in every case. The other area where metalogs do not work well are mixtures of densities with a gap in between. You can have overlapping densities, like in the trout data that I just showed, but if there's a gap in between the densities, that's harder for metalogs to deal with, and I'll show you why. So a typical example of a mixture of continuous and discrete distributions, it would be like a research and development project with a known cost and let's say a 50% failure probability, an uncertain commercial value if successful. So if you fail, you're going to get whatever is that known cost exactly. If you succeed and you get past your technical feasibility hurdle, then you commercialize your product, and there's a big wide probability distribution over how much money you will make or how much revenues you will get from this commercial product. Well, that distribution actually corresponds to a spike, as you can see on the left-hand diagram here, a spike at whatever was the cost, which has a 50% failure probability, right? And then the rest of this distribution corresponds to, if you succeed, then what is the commercial success probability. Sometimes it has sometimes you could actually lose money when you commercialize, and so that's represented by that part of the conditional distribution if it's successful. But as you can see with this distribution, if you look at the cumulative distribution, the CDF, you've got a part of the distribution below the actual cost, then you've got this vertical spike right at the cost of failure, and that has a 50% probability, and then you've got this long tail up here, which is commercial value if successful and if greater than the R&D cost. Well, what does that look like as a metalog? Well, you can see what happens here. The 2-term versus the 4-term metalogs, you'd have to say, if you look in here, these are a relatively poor fit to that particular shape. 5 terms and all the way up to 16 terms, it's really a very good fit. By the time you get to 16 terms, the metalog equation fits this totally beautifully. But what you'd see here, if you blew this up and looked at it, is the metalog is snaking around. It's going backwards and forwards and backwards and forwards like that. And a cumulative distribution function, by definition, cannot go back on itself and then forwards. Otherwise, it's not a cumulative distribution. Otherwise, it has a place where the density function is negative, and that violates the rules of probability. So for anything from 5 to 16 terms, this thing is infeasible. And so you would see a metalog panel that looks like this, where there are blanks in all those places. Now, what about a mixture of densities with gaps in between? This example was first brought to my attention by Lonnie Chrisman, who's the developer and the chief technical officer at Lumina Decision Systems. He developed the, oh gosh, what's their language, Sam?
Analytica.
Analytica, yeah, thank you. He's the developer of the language Analytica, which some of you may use. It's really excellent decision modeling software. Anyway, he came up with the skyscrapers example. That's what we call these twin densities here that are in the shape of the Twin Towers, basically, of New York. You got 2 uniform distributions that are, and you got a uniform distribution between 1 and 2, a uniform distribution between 3 and 4. And nothing in between. All right. Well, and that corresponds, as you can see, to this flat point, so this flat spot on the CDF. What does that look like? Well, as you can see, 2- and 3-term metalogs do fit this, but it's a relatively poor fit. And then when you go to 4 terms, 5 terms, you end up with a metalog equation, which is not a feasible probability distribution. It actually goes back on itself. All right. And so those things are not feasible probability distributions either. So the takeaway from this is whenever you have, just if you ever see a metalog panel where you've got very few feasible metalogs, then you do a quick check. Look for significant vertical or horizontal segments on the CDF. And usually what that means is there's some further modeling to be done or some further conditional representation. So for example, this distribution here, this R&D project, is actually extremely easy to represent if you start off with a 2-branch tree representing technical failure, and then with a 50% probability, and the other 50% probability is technical success, and then you end up with a conditional on technical success metalog distribution that looks quite beautiful and is very easy to represent. Similarly here, if you had an explanation for why you had maybe it's state of the world A that leads to this uniform distribution, and state of the world B, which leads to this uniform distribution, which could be a distribution upon which this is conditional. If you have outcome A, you end up with one uniform. If you have outcome B, you end up with another uniform. Then just modeling that with a 2-branch tree would solve this problem, and the metalogs would fit beautifully to conditional distributions.